Section 1. The first shock. Your clock is lying. Imagine your watch is slow, not by a minute. It is slow by years. This sounds like pure science fiction, but it is not. This is a fundamental truth about the universe. Time can slow down. For you, it can stretch and compress, depending on how fast you move and where you are. This is not just a quirky idea, it is a pillar of modern physics, proven by countless experiments. The steady beat of time you feel is, in a way, an illusion. It is not the same for everyone, everywhere. What does that mean for reality? Let's start with a simple, mind-bending hook. A twin becomes an astronaut and flies to a distant star at incredible speed. She returns younger than the twin, who stayed on Earth. It is called time dilation. First, let's tackle speed. The rule is simple. The faster you move through space, the slower you move through time. This is the core of special relativity. It follows from one unbreakable cosmic law. The speed of light is constant for everyone. Imagine a light clock. A pulse, bouncing between two mirrors. Each bounce is one tick. At rest, the pulse goes straight up and down, ticking steadily. But if the ship moves fast, an outside observer sees the pulse travel a longer diagonal path. Crucial idea. The light speed is the same for both observers. It cannot go faster to make up the distance. Longer path at the same speed means each tick takes more time, so the moving spaceship clock literally ticks slower. Not a mechanical error, time itself flows differently. This is not just a thought experiment. Scientists flew atomic clocks around the world. They returned behind identical ground clocks by tiny amounts, nanoseconds, exactly as predicted. At daily speeds the effect is tiny, but near light speed, the effect becomes dramatic. On a near light speed ship, time for the astronaut would pass much more slowly. And that is the idea. Speed is not the only thing that warps time. Gravity can do it too. This is a key part of general relativity. Rule: the stronger the gravity, the slower time flows. Massive objects curve space-time. Deeper in the well, clocks tick slower. Time runs slightly faster on a mountain than at sea level. The higher twin in weaker gravity ages a tiny bit faster than her sister, minuscule, but real and measurable. Gravity literally pulls on time itself. In a strong field, everything works harder to climb uphill in space-time, including time. Time slows down. Two ways to manipulate time: move very fast or get very close to something very heavy. These are not curiosities. They shape events from subatomic particles to cosmic structures, and your phone relies on both effects every day to tell you where you are. Relativity is not far away, it is in the palm of your hand. If you are skeptical, look at GPS on your smartphone. GPS is relativity in action, about 31 satellites orbiting Earth, each with an atomic clock. Your phone needs signals from at least 4 satellites and the exact arrival times. Tiny timing errors become huge location errors. 2 time dilation effects hit satellite clocks. Special relativity. Speed makes them tick slower by about 7 microseconds per day. General relativity. Weaker gravity up there makes them tick faster by about 45 microseconds per day. Combined, about plus 138 microseconds per day. Ignore that, and after one day you are off by over 10 kilometers. Engineers anticipated this. They preset and correct the clocks. So when you navigate, you are using Einstein. For real. You are proving that time slows down. Every single day. If the astronaut's clock and the Earth twins' clock disagree, which one is correct? It is not a true paradox. Both clocks are correct. There is no single universal time. Each clock measures its own path through space-time. The astronaut's high-speed path shortens her experienced duration. The Earth twins' path does not. Different roads, different distances. You would not call one odometer wrong. Time works the same way. Motion and gravity together define a world line. Elapsed time is the length of that path. Can we travel to the future? Yes. A near light speed trip that feels like 1 year to you might equal a decade on Earth. You aged 1 year. Everyone else aged 10. It is a one-way ticket. Physics allows forward travel, not return to the past. Time slows down, but never reverses. Now we arrive at the most extreme environment imaginable, the edge of a black hole. So massive and dense it carves an incredibly deep well in space-time. Beyond the event horizon, not even light can escape. From far away, your friend's clock slows and appears to freeze at the edge. Inside, their clock ticks 1 second per second. They cross in finite time. For them, the universe outside races ahead. Near a black hole, time slows to an almost unimaginable degree. What have we learned? Your watch is lying. Time is flexible. Speed and gravity warp time. The light clock explains it. GPS proves it every day. Time slows down. It challenges our place in the cosmos and fuels future exploration. Do one thing to make it stick. Ask a friend. If you could take a one-way trip 500 years into the future, would you do it?